Good morning, and thank you for joining us for the California Defense Manufacturing Community's program support to Space Foundry. My name is Ed Hendricks, and I'll be providing a brief overview of Nexflex and the DMCSP Cadence Grant program. I'll be followed by Amy Mueller, who will describe Nexflex support to Space Foundry under the Cadence Grant, and Dr. Gandhiraman, CEO and founder of Space Foundry, will provide the results and the impact of the program to his company and his efforts. And then afterwards, we'll have time for questions and answers. Next slide, please. So we'll be handling questions and answers afterwards, but we do have 3 different ways to ask questions. So once again, you'll have these opportunities later, and we'll show this slide again. Ultimately, at the conclusion of this, if you still have questions, you can email those questions to me. Next slide, please. So here's our overview for Nexflex and flexible hybrid electronics. Next slide. So Nexflex is one of 16 manufacturing innovation institutes falling under Manufacturing USA. Each of the manufacturing institutes have a common objective of developing an advanced manufacturing technology for the benefit of the American workers. And we're also one of 9 institutes that are chiefly funded through DoD, which means we have an added caveat that we're to support a manufacturing ecosystem that's relevant to the warfighter. Next slide, please. So Nexflex is a public-private partnership that was established in 2015. And since then, we've been going on pretty strongly. And again, we're funded primarily through DoD, but we're also funded through our membership. We're also funded through our membership, so we in effect double the investment of DoD through our project calls, which I'll go into more later. Next slide, please. So Nexflex has a number of different functions, and we'll go over them very briefly here and then dive into some of them a little bit more in the presentation. But first and foremost, we're a consortium of roughly 105 members, where we maintain the ecosystem consisting of universities, DoD agencies, and commercial partnerships. Again, all with the focus of advancing flexible hybrid electronics technology. We host webinars, workshops, and other networking events such as this. We have 11 technical working groups maintaining technology roadmaps and identifying gaps that will fill either through our work in our technology hub or the project calls. We host and direct and administer project calls where we close the gaps identified by the technical working groups, and as well as advance the technology in the best interest of DoD and, again, our ultimate mission of spreading flexible hybrid electronics. We also maintain a technology hub, which I'll go into much detail later, where we contribute to a flexible hybrid electronics learnings, but while supporting DoD projects and customer projects alike. And then lastly, we have a nationwide workforce development group that provides orientation to STEM careers for K through 12 kids, as well as assistance to workers, as well as an orientation to flexible hybrid electronics for DoD, as well as transitioning veterans. Next slide, please. Our consortium, as noted earlier, consists of roughly 105 members, these 105 members constitute the ecosystem for hybrid electronics. And they include OEMs and large defense contractors, manufacturers such as Jabil and Flex, equipment providers, material and component suppliers, universities and national labs, commercial contractors varying in size from very small startups to very large contractors. Next slide, please. Now to jump into a little bit of what is hybrid electronics or flexible hybrid electronics. Next slide, please. Flexible hybrid electronics, given the attributes, which we'll go over later, service a number of different market segments, such as medical devices and wearable devices, RF communications and antennas, satellite and defense and aerospace solutions, structural health and asset monitoring solutions, soft robotics, and automotive. Next slide. These translate directly to DoD relevant applications, again in the area of medical devices or physiological monitors, defense wearables, where we might use a device to, in this picture, monitor an environment and the physiological well-being of a soldier or airman. Applications with exoskeletons and soft robotics, where you don't need a lot of bulk, but you need to have, electronics intimately in contact with the patient. RF communications, where we print antennas directly on the surface of wings and without adding remarkably to the weight and Z profile of UAVs and drones. Asset and structural monitoring. These are sensors that are put on devices, whether they be aircraft or bridges or structures, that will monitor that item for structural health, giving insight to wear and tear of the vehicle and the vehicle performance. And again, these support aerospace applications because they're inherently lightweight and can be added to structures after the fact. And then lastly, for many of the same reasons, there are many automotive applications for flexible hybrid electronics. Next slide, please.
Ed?
Yes.
I'm sorry to interrupt you. This is Scott. GoToWebinar is telling me that the attendees are still on hold.
Oh.
Is Laura on the meeting?
Yes, she is.
I sure am. Let's see. It seems to be okay on my side, and we're being recorded. So let's see.
Bruce is raising his hand.
Oh, okay. All right, we're getting some comments. So I apologize. It must be my system that's wrong, but I didn't want our attendees to just be waiting for us. Sorry.
Okay. No,
yeah.
thank you, Scott. That would be
Thanks,
nice.
Scott.
That's nice to know.
Yeah, I think we're good. Thank you.
So early within Nexflex history, we wanted to come up with a project where we could not only demonstrate the attributes of flexible hybrid electronics, but also show the capability and maybe open up the vision of other people as to what they could do with this sort of technology. And so we took a well-known microcontroller, the Arduino Mini, and we did a direct conversion to a flexible hybrid device. And again, the intent was to go away from slideware, where people are imagining what an FHE device could be, and demonstrating exactly what an FHE device could be. And while at the same time demonstrating the capabilities and FHE attributes. So, for example, here we show a flexible hybrid or a flexible substrate. We show a completely additive process in terms of placing components onto that surface and printing the electronics and printing the circuits on that substrate. And that's also to demonstrate multiple layers and vias and dielectric layers, all in one package. That's functional and relevant to many applications. Next slide, please. Next slide. Oh, yeah, thanks. And so this led to an evolution of this platform, upon which we built up different projects. Some for DoD and some for commercial applications. And basically, we took the basic microcontroller platform, bumped up the capability quite a bit with a different microcontroller. We demonstrated low power Bluetooth connectivity. We printed antennas and basically expanded the applications per purpose, adding sensors in some cases and physiological sensors in other cases, and in other cases adding structural health sensors. Again, taking this basic concept of a flexible microcontroller and expanding the applications. Next slide, please. We also do more than just build devices and prove out concepts. We also evaluate materials, processes, and equipment with the end goal of characterizing each and finding the optimal application where that particular process or that particular piece of equipment is most relevant. Next slide, please. Within our technology hub, we have possibly the largest variety of state-of-the-art deposition systems or printing systems, such as screen printing, which is our workhorse of our technology hub, gravure offset. And by the way, many of these are printing techniques that have been common to the printing world, the newsprint world, for quite some time. But the application of these into printed electronics is somewhat new. We also have digital platforms such as extrusion and aerosol print capability. And a little bit more later on today, we'll be talking a little bit about plasma jet deposition with Space Foundry. Next slide, please. Also within our facility, we have a manufacturing integration area, and the workhorse in that particular facility is our BESI, where we do ultra thin die integration. That is to say, we'll take an unpackaged chip and we'll thin that chip down to the point where it also is flexible, and place that directly on the substrate, and the piece of equipment that we use to do that is basically the BESI. In the future, we'll be bringing up another platform which will also be capable of putting down the die and processing with an alternative methodology. And that's with our universal and adapting of the universal pick and place tool. Next slide. So if you'd like to have a virtual tour of our technology hub, you can go to YouTube and try searching Nexflex Technology Hub, and you should have a couple hits where you'll get to do a relatively current walkthrough of our technology hub and see some of the many pieces of equipment that we have there. Next slide, please. So now I'd like to take a little bit of time to talk about the Defense Manufacturing Community Support Program grant through the California Governor's Office. Next slide, please. The Defense Manufacturing Communities Support Program is designed to support long-term community investments that strengthen national security innovation and expand the capabilities of the defense industrial ecosystem. And under this program, the Department of Defense awarded 6 grants totaling $25 million under the Defense Manufacturing Community Support Program by the Office of Local Defense Community Cooperation. These awards follow a competitive selection process culminating under the Undersecretary of Defense for Acquisition and Sustainment. And under this process, the state of California, and specifically the organization within the state of California, Cadence, which stands for the California Advanced Defense Ecosystems and National Consortium Effort, was first designated as a defense manufacturing community, and then later awarded a grant of $4.9 million that was given to the state of California to provide this support. Next slide, please. So it was given to the state of the California Governor's Office of Planning and Research to undertake the project to facilitate the Cadence effort and enhance defense manufacturing in the state, particularly in the areas of microelectronics, 5G, and space. And under this program, our part of it is the Cadence Grant, which provides $600K of funding to Nexflex. Under this program, Nexflex will provide support to small businesses by providing access to cutting-edge flexible hybrid electronics development and manufacturing capability, and bring them into the FHE Manufacturing Innovation Institute ecosystem. So our objective under this is to support multiple small businesses by providing services that are tailored to each engagement's needs. And so some examples of this support are listed here, where we can do project plan creation, material evaluation and test, hardware design and software development, hardware evaluation, assembly, integration and test, documentation, and supply chain recommendations. Next slide, please. So at this point in time, I'd like to introduce you to Amy Mueller, who's a mechanical engineer and a program manager for this sub-project. And she's part of our advanced technologies group, and again, a mechanical engineer here at Nexflex.
Hi, thank you, Ed. I am Amy Mueller. I have the pleasure today of introducing Space Foundry's CEO and co-founder, Dr. Ram Prasad Gandhiraman. Space Foundry is an equipment supplier developing plasma-based printing technology for flexible and additive manufacturing. On this slide, I have listed a few of the key advantages of this technology, which Ram will be presenting in greater detail. Next slide, please. We have had the opportunity to participate in some previous collaborative efforts with Space Foundry, as I've demonstrated on this slide. Apologies for the fire alarms. Let me give it 1 second. All right. So by integrating Space Foundry's OEM module on our 6-axis robotic arm, we are able to together confirm that the print process does not rely on gravity. This feature, plus the ability to cure as you print, makes Space Foundry's technology a huge enabler of large non-planar print applications. Next slide, please. As part of the Cadence program, we at Nexflex were able to support Space Foundry through these 2 main tasks. So Nexflex supported the continued technology development by providing working space and resources at our technology hub in San Jose. With this regular access to our facility, it was included working alongside Nexflex staff and the ability to use test and characterization equipment found in our fab and test lab. We are also able to support the characterization of plasma jet printed samples by providing the design and characterization of printed antenna samples. And with that, I'm going to hand this over to Ram to talk more about Space Foundry and how the Cadence program has supported their efforts.
Yeah, thanks, Amy and Head, for the introduction and also for the opportunity to talk to the wider audience. So Space Foundry is, we are a hardware startup here in Silicon Valley. We are a spin-off of NASA Ames Research Center. I used to work on site as a contractor at Ames, and then spun off Space Foundry, licensed my own patents, and myself and my co-founder Dennis from Stanford, we both started this company. So we are currently selling equipments and are developing some very interesting solutions for printing a wide range of materials. We have few patents that are granted and several filed, and we are primarily funded by NASA SBIR. We have an ongoing active phase 3 SBIR. NASA has invested over $1.6 million so far in Space Foundry. And we work very closely with the groups from Marshall Space Flight Center and also Ames Research Center here in California. And we are primarily revenue generating through equipment sales. So we are actually focusing on emerging printed electronics market. So we are kind of not trying to displace something that is already well established and working. What we are trying to do with our technology is to enable new applications and enable printing on certain platforms which are very difficult to traditional way of printing. For example, we are working with an aerospace and defense company jointly through Nexflex, where they are working on printing on large aerospace structure. We print certain metal patterns onto these structures, and PlasmaJet has the ability to print in such large 3-dimensional objects fairly easily. And we are also in discussion with certain companies here in Silicon Valley to enable conformal electronics on their AR, VR headset, and also to enable some semiconductor packaging applications. And of course, in-space manufacturing is our core, vision to enable in-space manufacturing. So I'll kind of go through some of these applications. So printed electronics is an emerging industry, and there are certain issues associated with this industry. So some of them include ink, because there are really good printers that are out there, but they rely heavily on ink supply chain. The inks needs to be cured, and the metals generally oxidize in air, so the electronic property deteriorate over time. So it gets very difficult processing the ink. And then multiple equipment sets are needed when printing certain materials. And since we are actually printing on platforms that are generally not amenable for printing, like I mentioned in the aerospace structure, adhesion is a major issue. And printing of copper is one of the holy grail. So we're kind of focusing on solving some of these issues. And not to mention, this is, there are no liquid waste associated with these kind of materials processing, no nanoparticles, no toxic byproducts. So it's a fairly environmentally clean process. So what we're working on is called as plasma jet printing. Plasma is the bread and butter for semiconductor industry that is used for making chips, but they use very bulky equipment, mostly vacuum-based processing. What we have developed is like a pen, where the pen can write, conducting. You can basically write a circuit using this plasma pen. The advantages includes, it's a dry printing, so you don't have to cure. So you are kind of reducing some of these risks of oxidation issues associated with it, and it reduces the number of processing steps and also the materials cost. And as I mentioned, we use both off-the-shelf inks. We are kind of more or less, agnostic to the type of ink, so we can handle a wide range of inks. And at the same time, we have an in-house a water-based ink that actually reduces the supply chain issues significantly. And these inks have longer shelf life, and since there are no nanoparticles, so this becomes ideal for in-space manufacturing as well. So basically what the plasma does is, plasma is basically, it's different from blood plasma. This is a gaseous plasma. It's like your lightning discharge. It's happening at a very controlled environment, low temperature process happening within that print head. You introduce a gas, apply a high voltage, the gas becomes conducting, and then it basically helps, because of the electromagnetic field, all the particles in the printhead gets accelerated. So they go and bombard the substrate, and as a result, the adhesion is better. And then you can tune the electronic structure of these materials. These are kind of fairly known in semiconductor industry, and we are kind of adopting that process to this emerging printed electronics market, basically. So we have been selling equipment so far to universities and federal labs, and we are currently in discussion with some companies to see if we can do a printed service where we can basically scale the business in certain segments apart from selling equipments. Some of the examples, verticals that we are working on currently, the current focus in aerospace and defense is on conformal antenna printing. What you call a frequency selective surface as well. And the other application, as I mentioned, is in AR, VR, conformal antenna, and then early stage discussion with semiconductor and auto industries. And what we have demonstrated is that it turns out that plasma jet printing is going to be the only viable solution to enable embedded electronics on really large three-dimensional structures, which are very difficult to process with using conventional materials processing technologies. So we have demonstrated a wide range of printing so far since my days associated with NASA Ames over the past 10 years exactly now. But as a company, we are focusing on copper and silver. So this is basically a true enabler, a platform that can print a wide range of materials. And since we are a small company, we need to focus on a particular thing. So we decided to just focus on conductors, primarily copper and silver. Some of the examples of copper and silver prints that we have been printing using both proprietary ink as well as off-the-shelf inks. We have been printing antennas and Nexflex has been helping us in characterizing this. I will go through that. Wi-Fi antenna and X-band antenna on polyimide, and we have also been printing like some vertical patterns. This is very interesting. These are very early stage data that we have. So we are in discussion with semiconductor industry to see if we can use this for filling the vias for their IC manufacturing, for their chip manufacturing process. Here's a slide showing our integration of our print head into a robotic arm at Nexflex. So moving on to the space, basically, the technology was originally developed, as I said, at NASA Ames, meant for space applications, and we have been selling equipments, as a revenue generating to see somehow, we have to mature the product as we are working through NASA grants. So, we have gotten to a stage where the product is mature, and we recently demonstrated printing in zero gravity. I'll show that in the next slide. Our goal, Space Foundry's vision is to become an indispensable supply chain for any metallization need in space and in Moon. We have certain applications that we can really enable, like phased array antenna metallization and interconnects for solar panel manufacturing and alloys as well. We have the capability to print two different materials, mix them, create alloys and also metamaterials. So we will be working with some of our partners here, also with Nexflex potentially on Luna-based manufacturing as well. So our recent demo is actually very interesting. So I'm not sure if most of you are familiar with what is called as microgravity printing, zero gravity flight. Basically, this is to demonstrate that the technology works in zero gravity. There's a flight operated by a company called Zero Gravity Corporation. They basically run summer and winter campaigns to run experiments, primarily for NASA funded projects, or those companies that are interested in space applications. If they want to demonstrate that their technology works in microgravity, one of the easiest way is to take the product in this flight and demonstrate that it works during the microgravity conditions. So the way it works is the flight takes a parabolic path. It climbs up and then changes direction. While climbing up and then climbing down, the G value goes all the way up to 1.8 G. And then when it changes direction, there is a free flow for about 20 to 25 seconds. That's when you get to float. So we have to print in that window. So we have done that. So we took this printer into the flight. We have programmed it and then demonstrated printing in this flight. So here are some of the pictures showing us working in this microgravity environment. So it was actually we had a very challenging time. Like, we had actually 4 flights that were reserved. We had like intense plans for every day. And the very first day we go up, and then we lost the communication. Basically, the printer was not working. It was extremely stressful, and because of the flight takes 1G to 2G and 0G, some of the solderings get to loose, and then the electronics, the wiring that is sagging, that's going to pull, and it will lose the connections. So kind of understood that and then tried to fix. And then we also realized that 25 seconds is way too low, and especially if you are changing, you get from 1G to 2G, you get pulled, and then suddenly you get released, and then you float, and then again you get pulled on the ground. So it gets, the brain doesn't work, especially for the first 2 times, you are there. So we decided to go completely automated. This is a system that you see is like a lot of wirings that absolutely needed fixing. And then we addressed that, Marshall and Ames folks helped us, and then we actually visited Kennedy Space Center. There the payload people as well, they worked with us, and we solved that issue, and then we were good to go. And then we tested on the second flight, and then there was another problem we came across because of some pressure related issues. And then even the second flight didn't work, and then on the third day we were getting some partial success. We were able to get some decent prints, but as you can see on the right side, there were like a lot of droplet formation. These are totally unacceptable. So there was clearly, liquids are just dripping down at certain locations. So we decided to focus on that. We had like very few hours to fix before we leave the aircraft and then come back the next morning. So we fixed that, and then the final day we were able to get really good prints. Absolutely good, very successful, and some of the properties, what we see is actually way better than what you see on the ground. But so NASA has funded us a continued flight demo, and so we will be doing continuing some more studies in June this year to substantiate some of our claims and also demonstrate. These prints are all in 0G, close to 0G. So we will be demonstrating also in lunar G as well, because we are submitting a proposal for lunar-based manufacturing. Here's a video. It's of our thing. You will see that the first 2 days we have been kind of, the printer was not working. We had no idea what to do, and it was stressful. And then the day 3, day 4, you'll see us really enjoying, because in day 3 we had totally automated the process. We knew that we don't have time. Our brain doesn't work. Think. So all we can do is in that window we can only change the substrates. So we can, you could see us really enjoying in the last 2 days. So that's the day 1. Sorry, I don't know what happened. So in day 2 is where we had this fluid delivery issues, and there were no prints. We were disappointed. And then day 3, you see that one of our colleagues, Daniel, started puking. This flight is well known for, it's also called vomit flight. So because of this varying G, you tend to vomit, especially it's kind of stressful at some times. But we were still working. Daniel was still completely, you see that he's working, and then it started working, started printing in day 3, and then we really started enjoying, because it was like we were under intense pressure. Each flight, roughly about $50,000 that NASA had invested for each flight. So every flight we burned like 50K. And so we were under intense pressure to make it work. And then another aspect is it's a time sense, right? It was extreme. We just have limited time to identify and fix any problems. And same with day 4. Some of these days we were there in Florida for 3 weeks. Some of the days like just worked continuously for 36 hours. None of us went to sleep because we had to load the printer in the flight. And that's why you see the celebration going on when it's printing. It's a completely automated, so you can just print anywhere from the earth, basically. If you have internet, or if you don't have internet, you just use a Wi-Fi and print locally. These are some of the prints. These are all printed anywhere between 20 to 40 seconds. So the fact that we didn't have to do any curing, pre-treatment, post-treatment, and we got like amazing results, basically. It's like very promising. On the right, you see, it's called a scaling electron microscope. Basically, you look at the microstructure down to the 100 nanometer level. So what we see on the right is the samples printed on the ground, and what we see on the left is samples printed in the 0G conditions. And you do see that those samples printed on the ground, you get to like this globular growth, whereas on the in the microgravity environment, you do see, we don't know whether it's due to surface tension or what it is. You see a very kind of a really better pattern, better connection between these particles. And again, we have never seen such kind of bean-like pattern of particles that are printed in ground. Whereas printed in 0G, they tend to, as they are partially getting sintered in the plasma, they kind of form a web in a well-connected network. Some antenna characterization were done by Nexflex. We are a really very small team. We have been primarily focusing on developing the hardware and the process of printing. So Nexflex has been helping us in getting the antenna designs and also the characterization. Some of these silver prints, the resistivity were just 10x higher than the bulk, which is very promising. We have never gotten this result before for the samples that are printed on the ground. Here's some press release on our success. So the way we are going, the future for this technology is that we are working with NASA, to see if we can get this printer installed at International Space Station within the next 24 months, 18 to 24 months. We are hoping to have it installed by 2024. And it enables on-demand manufacturing of electronics, and we aim to become an indispensable supply chain for any off-Earth manufacturing. We are also in discussion with some other large startups that have raised a ton of money for space manufacturing. So we are currently being under the radar, so that at least, if and when they need certain materials processing, we will be able to do that.
Excuse me, Ram.
Yes.
We're having a little bit of a connection issue could you speak a little slower? That might help help some of the
sure.
audio. Thank you.
Sure. Yeah. We are really hoping to have our presence in ISS and also on lunar surface in the coming years. Nexflex's help has been incredible because we are just a small team of 4 people. We are not funded by any VCs, primarily NASA SBIR and some sales money. So we were really short of space and equipments we couldn't afford. So this Cadence program has been absolutely helpful. It really helped us accelerate the entire process development because, as I said earlier, we were under severe time crunch for our flight demo. So we continued doing the printing process both in our location in San Jose and also at Nexflex. We are just only 10 minutes away from our lab. And we also got access to some of the characterization tools and also personal people who have been helping us has been on a regular basis. Alex Cook, Amy, she's on the call here, and Mike Avanel as well. And we also have Michael Orrill, sorry, I haven't mentioned here. So few staff that we have been engaging at Nexflex. So this one is what's called as a 4-point probe. Again, we don't have these tools, so all of these facilities we're using at Nexflex to measure the conductivity, to see how good the electrical performance of the samples is. And this one is what's called as a confocal microscopy image. Basically, it's a very high resolution microscope. These are all very much needed to evaluate how good or bad the film characteristics are. And this one is, is our printer there at Nexflex. In addition to the robotic arm, we also have this standalone printer. The last few slides is our story, just if you have a couple of minutes. Basically, we have been keeping up the Silicon Valley tradition. We started off at CTO's garage in Menlo Park. So when we started the company, we knew that we were not sure which way we should go, whether we should sell the equipment, make some printed useful products. We're not sure. Right, and all of a sudden, people from Sandia National Lab reached out to us, and they wanted to buy the equipment. So we, we got our first purchase order while we were still at the garage, and then we started making the machine, trying different ways. We realized that there's really a lot of parts that we really need to validate, and we needed to do an intense research and development work. A lot of it was done in the garage in the early days, first a couple of years. We decided to do everything by ourselves, like including wiring, soldering, assembling all the gantries. So we hired some students from Southern California, Cal Poly. Absolutely brilliant, highly motivated. They really helped. All of this you see was done in the garage by these 3 girls, and there's one other guy. Really good actually. So and we kind of started seeing getting more orders, and then the customers wanted to come and visit us and see how good the product is before issuing us the purchase order. So we had customer visits to the garage, very unusual. They were happy, and right away, some of these people were willing to give us upfront money. They knew what it is, so they understood, and then they were willing to give some money upfront so that we can buy the parts and pay the salary for some of these employees. First system was shipped to Sandia National Lab, and then we have been kind of maturing the product over the past few years. The product has taken really different shapes. We now feel that we are advanced. We need to freeze all the design and just focus on improving the print head and printing. So that is what we are doing now. And these are some of the customers where we integrate, install the printer, and we just shipped one other printer to UK in University College London. They received it yesterday, and I'll be flying next week and doing the installation. And then we are also installing one other printer at Indian Institute of Technology in Kanpur, and we are expecting some more purchase orders from universities in East Coast and also from Australia and New Zealand. So we are kind of, making global impact thanks to all the people who have been funding us. And as I said, very small team. We are 4 people, and thank you very much. And as I said, like Cadence, Nexflex has been extremely helpful for us. And we really look forward to working with you all to get continued support. Thank you.
Well, thank you very much, Ram. I really appreciate the update on Space Foundry, as well as a little bit of the details of how the Cadence project or Cadence Grant supported your efforts to commercialize and demonstrate functioning of your standalone plasma jet printer. At this particular time, we're going to open this up for questions. And again, as a reminder, if you'd like to enter a question, you can either enter it under the questions pane, or you can raise your hand and we'll have you ask your question online. And then once again, if you want to save your questions for later, you can always email me at ehendricks@nexflex.us.
Ed, I'd like to ask a question.
Oh, yes, go ahead, Malcolm.
Okay, this was a lot of information, Ram, and a lot of interesting stuff here. Way back at the beginning, you had a graph, which was a bell-shaped graph about obviously printing at various altitudes. Is there any way you could go back to that?
Yeah.
No, that was the one. Yeah.
Yeah.
Okay, I didn't quite understand that. This is altitude versus maneuver time seconds. And I didn't quite understand what that meant.
So basically what happens is that, you know, it flies under the altitude is kind of, when you say 0G, you get the condition, it doesn't really go up all the way to 0G, you know, to the low Earth orbit or anything. It flies in the same altitude as any other domestic or international flight will fly. So that altitude is, you know, it goes maximum 40,000 feet. So the way you get the 0G is basically when you have this, when you go through this parabolic route, a sudden, you know, a ramp, and then change the direction. In that time, you get a certain 0G thing. So it's, so that's what, like, so you get the x-axis, you see like 20 to 45. It's basically 25 seconds of 0G you get when you know, when during that parabolic route.
So that's flying at the same altitude, you get 0G.
Yes, just by changing the direction.
I don't quite understand that, but anyway.
So it's, you know, because there is a sudden, you know, it ramps up suddenly where you go from 1 to 1.8 G, and then the aircraft just, you know, it suddenly changes direction. And when it does, you get that floating 0G in you know, when it changes the direction in that parabolic route.
But does that mean you've only got 25 seconds to print?
Yes, so we get about 30 times. So the flight keeps going up and down, up and down. So you get about 30 times, 25 seconds. So we have actually, you know, so that's why we programmed it completely so that the printer prints during that 25 seconds. So you can see here, I have the presentations.
Now, do you have to initiate that printing cycle, or did you already program that in so that it would go off when certain conditions were met?
Yes, yes. So we can have that basically programmed. We use a G code and M code. So what you see here, basically the green is where the printing took place. Out of 3 columns, 1 column is time in seconds, and the second column is the gravity, and the third column is the position. So you can see that in the first section on the left, the red denotes lunar, no, it's Martian, 0.4. Yeah, the red denotes Martian gravity. The G drops from 1.1 to 0.4, 0.3. And the printing took place only in that green portion, 10 to 16. And then the orange corresponds to lunar G. You see the G drops from drops to 0.1, 0.15. The printing happened only in that green portion. And then these are 0G. So basically in that, depending on how they maneuver, they can get lunar G, Martian G, or close to 0G. So you see it hovers around 0G. All the green indicates that's when the printing took place. So the way we did this is that we had what is called as, I think I have a, yeah. So what we call as, there's a parking site. The printhead goes to a park site or a dump site, and it waits. We programmed it basically and connected it with an accelerometer. So when the accelerometer sees that the gravity changes, then it will turn on every part of the printer, and then it will wait until it sees 1.6 G. And then once it goes to 1.6 G, there is a sudden drop to closer to 0 G. So that happens, so we said, okay, we will kind of program it in such a way that when it sees 1.6 G, then the printhead will go to the dump site, it will activate everything and wait for a few seconds, and then it will start printing. So that's a very clear pattern.
I'm sorry, we have several additional questions that I think it'd probably be helpful to read out to you, if you don't mind the interruption.
Sure.
I'll summarize for you. There are several that relate to ink properties. Questions about, well, first, where can people obtain more detailed property data on the materials that you can deposit? For example, copper, silver, properties like DC resistivity, surface morphology, high frequency loss, thickness, as well as dielectric materials, edge and structural properties of the prints, things like the edge sharpness, microstructural density, and things like that. That seems to be a pretty common question that several people have asked.
Yes, I think that's so basically we can work with both off-the-shelf inks, and we also have this proprietary ink. So with off-the-shelf ink, some of our customers are developing, they're working on some publications, and we are also working on a couple of manuscripts. It's still in pending stage, but we would like to as you see, there's some work that is needed in terms of resolution, line with all these things. But what we are currently doing is trying to get the surface roughness, the conductivity, and all these data given the state of the print head is, without trying to improve the print head, go to 700, go to like 50 micron or 20 microns. And our priority is to get these conductivity numbers. So currently for copper, we are somewhere about 60x the bulk resistivity. And for 0G silver, printed silver, we are about 10x the bulk resistivity. The next few weeks, we are gonna, do some consistent printing and get these data out in the public domain.
Do we have some additional questions?
Yeah.
So Ram, thanks for those answers. Is there a place that people can go for additional information? Should they contact you, or do you have information on your website?
Yeah, I think as of now, just reach out to me. I don't know, website is still, I think, no, we don't have much information on the website. Feel free to reach out to me, absolutely. I'll get back immediately. My contact details are here. Oops, yeah. Feel free to reach out to me anytime. You are people here, anytime you are also welcome to our facility. We are located just 10 minutes drive from Nexflex. We also have a printer at Nexflex, so we will be able to give you a demo at Nexflex as well. So yeah, you're welcome basically anytime to our facility.
Ed, that is all the questions that I see right now. Oh, I'm sorry, I take it back. There's one that I missed. There's a question about overspray and satellite droplets along the printed traces. Do you have them and how can you control them, things like that?
Yes, so we do see a overspray. So we are actually working on getting the process. You see some of these lines. So we really need to optimize the process. If you zoom in this picture, you will see on the antenna printed on the left or on the copper antenna, we do see have some overspray, and I think we feel like it has more to do with process condition optimization, because we need to have a right amount of gas and liquid inlet entering the substrate and work distance and things like that. And so we need to do some work on controlling the overspray. So the satellite droplets we don't see. I think we have figured out a way to control the droplet formation. At the moment, it's the overspray that we are trying to address.
There's been another question, if you're willing to field one more, just came in. Could you say a little more about the students you engaged from Cal Poly, and with whom did you work? I think that may be referring to faculty. And what kind of arrangements did you have?
Oh yeah, like it was actually they were the best, seriously. They had so much confidence in them. I tried to reach out to them to hire. Unfortunately, I think they're all already working in some other company. So one of our early hire, the first hire, Arlene, she actually was interning at NASA in my lab. So that's how I reached out to her. So she joined us. She had to take a career break for personal reasons. So she joined us. She's been extremely good. And then I told her, like, we really need some people. She basically reached out to her friends. So we had no contact with any faculty from Cal Poly. They had all the students that we had, like they had like, so far we have had 4 people from Cal Poly. All 4 of them absolutely good in terms of the confidence or the technical capabilities that they had. There's another guy, he just joined Google recently. So I don't have any working relation with any faculties over there. The person that you see on the left, Arlene, used to be our #1 employee. Yeah, and then she brought those two girls, and then another person joined us, Jason. Yeah. Unfortunately, none of them are with us now. I've been trying to get hold of them, but I think looks like all of them have settled in a nice job. And given the uncertainty around startup, that's another thing. We work. It gets very difficult since we are not VC funded. Our runways are not like we cannot commit for like 2-year, 3-year runway. So it gets a little bit challenging to retain some of the talents. At the end of the day, people do want more or less like a stable income, right?
Yeah. All right.
And I'll be happy if anybody have any working relation with any Cal Poly faculties that would want to work with us. Obviously, we have like out of 4 people, we have 100% success rate in terms of hiring. Sometimes in a very early stage startup, a wrong hire can really kill us. Can really take us back by several years. Kind of, yeah. Yeah, currently it's all men's club now, unfortunately.
So if we don't have any further questions, I'd like to take this time to thank Ram for sharing a wonderful video, as well as sharing the information regarding how to regarding the advancement of your standalone printer and in the latest and greatest in the support that you've received from the Cadence Grant.
Thank you
once
so
again,
much, Ed. Yeah.
and once again, if you have any questions, you can direct them to me, and if you didn't catch Ram's email address, I can always forward those over should you need to. I wanted to share a little bit more about the Cadence projects. As we mentioned, the Cadence program consists of several projects, only one of which is a Nexflex project. And so this slide talks about some of the various projects underway. Please advance to the next slide. And then the other 15 from various organizations within the Cadence community. Next slide, please. And if you have any further questions, you can direct those to me, and I can direct you to the appropriate Cadence point of contact if you're interested in learning more about the various support that can come to small businesses within the state of California. Once again, thank you everybody for attending this webinar. Once again, it will be online for later viewing, and we'll let you know the location of that posting. And once again, thanks for attending, and look forward to future webinars regarding the Cadence Grant program.
Thank you, Ram. That was awesome.
Thanks.
Thanks a lot, Ram. Thanks, Ed and Amy. Bye, everybody.
Bye.
Thanks.
Take care.
Bye.
Thank
Bye.
you.
Bye, everyone.